Okay, so finished supper. Continuing with the answers to the questions. Number 42 says a student flings, that's a weird word, flings a 23-gram ball of putty, so like silly putty, at a 225-gram cart sitting on a slanted air track. Boy, this person is bored. They must be in isolation. All right. So, a student flings a ball. That is 23 grams. At a 225 kilogram cart. So the cart is 225 grams. It's sitting on a slanted air track that is 1.5 meters long. So the track is slanted and it's 1.5 meters long. Okay. The track is slanted at an angle of 25 degrees with the horizontal. If the putty is traveling at 4.2 meters per second, so parallel with the track when it hits the cart. So here's the cart, and the putty is moving parallel to that. The question is, will the cart reach the end of the track before it stops and slide back down? So the question is, so they fling the putty at the cart, it hits the cart goes up this track. The question is, does it get to the end of the track? The track is 1.5 meters. So really the question is, how far up the track is it going to go? That's really what we're looking for. So what I did, I'm going to move my answers over here so I can see them a little bit. So what I did again was I talked about the momentum just before and the momentum just after the ball of putty hits the cart. So I talked about the momentum before. And before, the mass of the ball of putty is 23 grams, which is 0.0023 kilograms. Nope, 0.023, too many zeros there. So 1, 2, 3, yeah, 0.023 kilograms times the velocity. I don't know what that is. Plus the mass of the cart is 0.225, but the velocity of the cart is nothing because it's just sitting there minding its own business. Afterwards, oh, this is not unknown. Whoops. It said that when it hits the cart, the velocity is 4.2, so that's not unknown. That's there, 4.2. Helps if I pay attention to what I put on the board, doesn't it? Okay, so once the ball of putty hits the cart, they stick together. They're one thing, so I'm going to add them together, which is going to be 0.248. But I don't know the velocity. I don't know that. So what I'm going to figure out is I'm going to figure out the velocity. So that's gone. So I'm going to have 0.023 times 4.2, and then I'm going to divide it by 0.248, and I got 0.3895 meters per second. Okay, so that's velocity, but that doesn't tell me how far it's going. And also, once it hit, that's how fast it's going once the ball of putty hits the cart. But as it goes up, it's going to slow down. So again, I need to think about kinetic energy. At the bottom, it's all kinetic energy. As it goes up, it slows down. Wherever it stops, whether it's at the end or not, wherever it stops, it has all gravitational potential energy. So at the bottom, I'm going to have kinetic energy. At the top, I'm going to have gravitational potential energy, and energy cannot be created or destroyed, and they said it was frictionless, so nothing is being lost to friction, so therefore those have to equal. So 1/2 mv squared is equal to mass times gravity times height. Again, the mass doesn't change from the bottom to the top, so I can just cancel those out. So I have 1/2 times 0.3895 squared is equal to 9.81 times height, because height is what I want to know. How far up this track is it going to go? So once I figure that out, I got that the height was 0.0077 meters. But that's still not the answer, because what I found was a height, the difference between when it was at the bottom versus when it stopped. I got the height was 0.077. I want to know how far up the track it goes. So I'm actually looking for the hypotenuse to this triangle. So if I know this angle, and I know the opposite side, and I want to know the hypotenuse side, that would be sine of 25 is opposite over hypotenuse. So that means once I rearrange 0.0077 divided by sine of 25, and I got that it was 0.018 meters. It said that the track was 1.5 meters long, but it's going to stop at 0.018 meters. It's not even going to make it close to the top of this track. So will it reach the top of the track? No, it will not. All right. Number 43. Number 43. Next one. And then I will probably start a new video so that they're not super, super, super long. 43. Let's look at 43. What does it say? 43 says we have a car again. All right, so a car with a mass of 1,875 kilograms, we're going to call it car A, is traveling along a country road. The driver sees a deer dart out into the road. The driver slams on the brake and manages to stop before he hits the deer. But there's a second car. The mass of the second car is 2,135 kilograms. And he was kind of tailgating the other guy. And he didn't see the deer. All he noticed was the guy in front of him slammed on his brakes and came to a stop. But he didn't have time to stop himself because he noticed too late. So when the driver realizes that the car ahead is stopping, he hits the brake, but he can't stop. The cars lock together and they skid another distance of 4.58 meters. All of the motion is in a straight line. So like car A is going this way, car B is going this way. They hit, they lock together, they still slide that way. They don't slide off to an angle or anything. If the coefficient of friction, there's a lot of information here. If the coefficient of friction between the dry concrete and the rubber tires is 0.750, what was the speed of the second car when it hit the stopped car? So we know that car A was stopped because it managed to avoid the deer. What we want to know is, how fast was car B going when it slammed into the back of car A? That's what we want to know. So, we have to think about some of this. Now, here is what I did. So we want to know this, okay? So Again, we're going to look at the momentum right before and right after. Again, I'm going to try and go right to what would be my last step and show you why you can't do that, okay? So what I would want to do is I would want to look at momentum right before the two cars hit and right after the two cars hit, because that's the only way I can figure out how fast it was going right before it hit the other car. Because remember, he's looked up, he was driving along, he's looked up, he's seen the other car stopped, he's slammed on the brakes, so he's in the middle of slowing down. So sorry, I've got a dog hair on my nose. So his velocity is changing very, very rapidly. So I want to know the instant before it hits, before he collides, how fast is he going? So before, mass of A is 1,875. Velocity of A is nothing because he's stopped for the deer. Velocity of B is 2,135, but I don't know the velocity of B. That's what I want to know. Now, it says that after they hit, they lock together, which means I need to add the two masses together. So when I do that, I get 4,010. And I have to multiply that by how fast they're going right when they hit. I know eventually they're going to come to a stop, but I need to know how fast they're going right after they hit. So the problem is I have two things I don't know in here. I can't do that. So I need to figure out one of those two things. I don't have the ability to figure out this one. I do have the ability to figure out the velocity of the two of them right after they hit. Again, by thinking about my energy, okay? So when they hit, it's all going to be kinetic energy. When they hit, it's all motion. It's all kinetic energy. But when they finally slide to a stop, they don't have any energy left. But remember, energy can't be created or destroyed. So where did it go? Well, we lost it. It dissipated in terms of in heat because of the friction between the tires and the road. That's why your car stops, is friction between the tires and the road. So it has to equal the work done between the tires and the road in order to stop the cars. So kinetic energy is 1/2 mv squared. Work is force times distance. But what kind of force is going on? Well, I just got done saying the only force that's stopping your car, this freaks me out when I say it, but really, when you hit your brakes, the only force stopping your car is friction. That's it. That's why your car stops better on pavement than it does on ice, because there's more friction. So, force of friction times distance. So let's start filling in some numbers here. So 1/2 mv squared, and I don't know v, but mass I know is 4,010. Force of friction is coefficient of friction, right? Force of friction is coefficient of friction times normal force. But normal force is pushing up, force of gravity is pulling straight down, so it's actually a coefficient of friction times mass times gravity. So coefficient of friction, they told me, was 0.750. Mass is 4,010. Gravity is 9.81. And my distance is 4.58 meters. That's how far they travel before they stop. Now again, you can leave that 4,010 for mass in there, but I have one on this side and one on this side, so I just cancel them out anyway. So I do this times this times this, and then I multiply it by 2, and then I take the square root because I know how to do algebra, and so do you. And I would get that the velocity is 8.21 meters per second. So that is the velocity of the two cars when right after they've collided, which goes here. Now I have the ability to figure that out. So that's gone. So I do 4,010 times 8.21 divided by 2,135. And I got velocity of B was 15.4 meters per second. And if you were really curious, you could change that into kilometers per hour and see how fast was that person actually going. And 15.4 meters per second. So there's, in 1 kilometer, there's 1,000. So it would actually be 15.4 times 3,600 divided by 1,000. The person was going 55 kilometers an hour. If you get rear-ended at 55 kilometers an hour, that's going to hurt. All right. So that was number 43. So I've done 2 examples. I'm going to start a new video just so that the video is not a million hours long. Just a sec.